So here we're told that this radioactive substance decreases by 17% after every 20 years, which means that after 20 years you'll have 83% of the original. And we're starting with 100 grams, so after 20 years it's going to be 100 times 0.83 or 83 grams. Now, with another 20 years, it would be this amount times 0.83 because it's 83% of what's remaining. So you'll see the pattern would be 100 times 0.83 to the power. Now, these are going to be in multiples of 20. How many 20 years multiples? So this is going to be t over 20. So after 40 years, this would be a square. So that's the expression. We look at the choices. That's actually the first one, a of t. What they're now asking is, according to this model, 30 grams of the substance will remain after approximately how many years? So what they're saying is this is equal to 30 after what value of t? So we can compute this. This is going to be, if I divide both sides by 30, or you can plug in a value as well. Either way, for example, I know that if it's 40, we just did this because it's about 83, and then if you did another 83%, it's about 64. So it's 8 times 8, a little bit more maybe. So I know after 40 years, it's going to be up around 64. So I'm going to actually try 76, meaning I'll plug in 76 in the answer choice and see what I get. So 76 divided by 20, so that's 3.8, and then I have to raise 0.83 to the power of 3.8, sorry. So I get 0.492 multiplies, I get about 49. So that's clearly not the one, so we know the answer is 130. But let's make sure. At this point, this is just calculation. So 6.5 is what I get. So I have to raise 0.83 to 6.5, and yeah, I get 29.8, which is about 30. So the answer is 130. You can also use log to find this directly, but I think it's easier to just plug in here, having some idea. So the answer is you fill in this one for the function, and then this is the number of years.